All right, thanks, Jenny. And before I get going, I'm glad to be here today or there today virtually. I'm sorry I'm not able to be there this time around in my old haunt of the LPI and seeing friends and colleagues, but that's how it goes. So thanks to Zoom. Let's get this started. Let me share my screen and please give me a confirmation that you can see it.
Yes, we see it.
Excellent. And as you said, Jenny, this is a very broad topic, and I think most of us could imagine creating just a full graduate course on it. But today my goal is to bring in talk about some of the major tectonic features of Venus and in context of geodynamic models. Let's see, can it advance? Come on, advance. There you go. So here we are, 29 years after Magellan, and let's hope it's not going to be 10 more years until we get new data. But Venus has been a tough nut to crack. And in part, the reason is that its surface is very rich in tectonic and volcanic features. Their relationships are not entirely clear from the data sets that we have. And the limitation comes from the resolution of those data sets. The image resolution, we all know, 75 meters, so we can't really see anything much smaller than 200 meters or so. And the disparity with the resolution of the topographic data complicates matters. But with that said, at the end of the Magellan, there was a relatively widespread view that Venus is currently inactive under a stagnant lid regime, where the crust is extremely strong due to its anhydrous state. But the question is it really? Tectonics encapsulates the behavior of the boundary layer of the Venus or a terrestrial planet's thermal system, where heat is trying to escape from the interior to the exterior. Solomatov and Marazi showed a variety of convective regimes where we have a small viscosity contrast leads to a thin lid in a convective regime where the lid is participating in convection. And then as the viscosity contrast increases, the lid becomes thicker. There's a transitory regime there into a greater viscosity contrast where the interior is still convective, but the boundary condition is now thick and stagnant, and heat is being conductively transferred to the surface for its radiation. More put that in the context of an evolutionary path of terrestrial planets that go from a magma ocean when there's a lot of heat flux and hot temperatures into a heat pipe regime, perhaps a plate tectonics regime, a transitory into a stagnant lid regime. Rolf et al. Put that in context of modeling using the surface yield stress of the lithosphere as well as the effectiveness of eruptive heat transfer, and classified the different numerical regimes here into the different geodynamic regimes. You have a mobile lid, an episodic lid, stagnant lid, the squishy regime, and the heat pipe. And we know that the different geodynamic regimes are going to have different tectonic signatures at the surface, as the diagram here on the right shows, between the mobile lid and the plate tectonics and the squishy lid, for example. Now, before we keep going, we need to quickly review here the major physiography of Venus. We have the tessera and the crustal plateaus. We see here they're elevated in red in the topographic rendition of Hansen. And we have volcanic rises, plains with various types of tectonic deformation. Corona, Ishtar Terra, and Artemis. Ishtar Terra and Artemis are what I would consider beasts of their own class. So I'm really not gonna talk much about, well, I'm not gonna talk about them. I'm gonna concentrate on tessera plains and coronae, And given that volcanic rises are dominantly volcanic in nature, I will not touch on them either. So with that said, plains. We all know that the plains make up the majority of the surface of Venus. They're predominantly low standing. They have a crater population that is insufficient to determine whether the plains were emplaced all in a catastrophic short durations resurfacing event, or if the plains have been in place gradually over time in sort of an equilibrium state. So we see here a statistical model of Hawk et al., where they separated the plains into different portions. And what we can see from this modeling is that you can, with 2 sigma confidence, separate 2 populations of plains, one older and one younger. Yes, is there a question there? No, just background noise. Okay, continuing. So we have these 2 populations, and I like this rendition of Riedel showing the different kernel densities for their modeling of the distribution of craters. So you can clump different areas according to the crater population. Now, gravity data indicates that the plains are bottom loaded, thus imposing a compressional regime at their surface. Lawrence and Phillips used genetic niching algorithms to invert the gravity data and show that both volcanic rises and plains are bottom loaded. As you can see, there's 3 examples here of Atla, a volcanic rise, and Atlanta and Lavinia plains units. And both have compensation deep in the mantle. So that means that there is a dynamic component to their compensation of the surface topography. However, Atla, being a volcanic rise, has a negative density anomaly, meaning the bottom load is upwards, while the plains, the density anomaly is positive, meaning denser, and the bottom loading is negative, downwards. So you can see here in this diagram of Phillips and Henson just an idea of the plains being over areas of cold mantle downwellings and being bottom loaded in that way. Now, the tectonic deformation at the plains are either distributed or concentrated. And we see that in this map of Bilotti and Subi. The distributed formation is dominated by wrinkle ridges, and their mapping of the wrinkle ridges you can see now in this map as shading here of wrinkle ridges. So there are areas that are very dense with wrinkle ridges and areas that are not so dense. And the concentrated deformation exists as either ridge belts or rifting and groove belts. And you can see the rifting belts here in this shading solid gray. Some have worked to put the different types of deformation in the plains in the context of a directional evolutionary path of Venus, going from a global tectonic regime to a more concentrated tectonic regime, as Ivanov and have done here. So they used different types of tectonic signatures of the plains, such as wrinkle ridges here, as we can see in this middle figure, to define these different plains units or tectonic units and put in context of these deformations over time. Some others have used coupling between the climate and the tectonics using excursions of surface temperature and how they affect the stress state of the crust, or especially the upper crust, into an extinction or a compression regime. So if Venus underwent a surface temperature excursion due to climate change, a heating episode, for example, you underwent a compression regime, and as Venus cools off, it transitions in an extinction regime. And so moving to the focused plains deformation, here are the 3 examples of the major belts, the extensional belts being the groove or lineas, and the rifting as chasmata, and the contraction as the ridge belts or dorsae. shown by Ivanov and Head. And when you map these belts on the surface and start looking at them as an interconnected system of belt deformation, you have clues, perhaps, that the crust of Venus, the lithosphere, is divided into small blocks, as Baron et al. Showed in 2021. And if these are indeed blocks of undeformed crust surrounded by areas of great deformation, then it is indicating that there's limited but widespread lithospheric mobility that has occurred on Venus. Now, shifting to coronae, now that we've got an indication from the planes that there is potentially a deformation and mobility, challenging that view of a stagnant lid planet. Corona, the basics, everyone here in the room probably knows, but just bringing up anyone that needs to be brought up to speed, they're circular to elongate volcanic tectonic features. They have variable tectonic signatures. Some have profuse tectonic features, faulting, maybe dike swarms. They have variable topographic signatures, as this diagram of Smucker and Stofan shows, from some that are topographically depressed, some with very little topography, some that are plateau-like, rimmed, etc. But they all have ubiquitous volcanism in the form of flows or small shields, and their diameters range from about 100 kilometers to many hundreds of kilometers, and you see that the modal distributions here are in the few hundreds of kilometers for the diameter of coronae. They can be divided into two types of coronae: those that have very strong tectonic features that delineate their rims, as here in the bottom right. Those are known as type 1, and those that have very little tectonic signature, and their circumference is very poorly delineated by tectonics, and those are the type 2. But they all still have quite a bit of volcanics. It is commonly accepted that coronae are formed by the interaction between rising mantle plumes or blobs with the lithosphere, whereas the plume rises and impinges upon the bottom of the lithosphere, it creates intrusive melts. And you see some modeling from Smucker and Stofan and Dunbar about this process. The coupling of this upwelling lateral flow as it spreads out at the bottom of the lithosphere may induce some delimitation at the edges of the coronae. And this could be sites of localized crustal subduction. In addition, these coronae tend to preferentially occur where rifting belts are present. Not entirely, but there is a preference for occurring at those localized deformation belts. And a recent study of Smucker et al. Showed that the heat flow at coronaes near rift tends to be higher than coronas in other areas. And as a result, the lithosphere in rift coronae is thinner than the lithosphere elsewhere. Gulcher also modeled or interpreted the different morphologies of coronae as an evolutionary path, and interpreted as coronae that are potentially active versus coronae that are potentially inactive. So together, these new views of corona, squeezing the Magellan data a little bit further, putting new ways of interpreting the data, suggest that Venus is not in a stagnant lid regime, but perhaps in a squishy lid regime, with morphology possibly as an indication of current activity. So with that said about coronae, let's jump to tessera, and I'm going to probably spend a little bit more time in tessera because that's what I've studied more at length. in my Venus career. So originally dubbed as parquet, tessera was originally defined as a highly deformed terrain with at least two intersecting tectonic trends, having both compressional and extensional features. So one of the early papers outlining tessera was Barsukov using Venera 15 and 16 tessera, SAR images of tessera. And you can see here the same area with Magellan data. So you can see the different intersecting trends. You have extensional features, graben, and you have compressional features as folds here in this area, as well as some intra-tessera planes units. Now, most of tessera in terms of area is bound by elevated crestal plateaus. But if you look at tessera as a number of features occurring on Venus, the most numerous are small inliers that are embayed by planes, as this map shows by Ivanov and Head, and their distribution of tessera number. Relatively small tessera are more numerous, but most of the areas captured in large plateaus. But as a group, they correspond to the oldest stratigraphic unit on Venus, the oldest terrain on Venus. But the fact that you have these inliers and the large plateaus and an embayment relationship is prevalent around the tessera margins, the question arises, does tessera vastly expand beneath the planes? Is it a marker unit delineating a past tectonic regime of Venus? And these are still outstanding questions. When we look at tessera, we know, however, that tessera is not the same. There are different tectonic signatures, different features and arrangement of these features for different tessera in different locations. So here, Hansen and Willis codified some of these different types of tessera that we see at different areas of Venus. And mapping the different features indicate different stress regimes and different evolution of the different areas of tessera. So tessera is not all alike, but they all have, quite a bit of tectonic features, highly deformed and high radar backscatter. Now, given that most of tessera is in crestal plateaus, we need to look at crestal plateaus. These plateaus are hundreds of kilometers in radius. They stand several thousands of meters, from hundreds to several thousands of meters above the surrounding plains. Some have different topographic signatures from others. Some have an elevated rim, while others have their central core more elevated than the margins. And there are different types of tessera and tessera arrangement around the different crestal plateaus. So Hansen and Banks created this average look of crestal plateaus where the interior has the basin and dome tessera. You have intra-tessera basins, a marginal belt type of folding belt type of tessera with radial large and small grabens. Gilmore and Head looked at Tellus, for example, and mapped the different types of tessera and identified the marginal fold belt type of tessera at the edges of Tellus. And their interpretation is that Tellus evolved from the accretion of different tessera blocks over time, indicating potential mobility of the lithosphere during the formation of tessera. And here on the right, you see the different topographic regimes or signatures of tessera, crestal plateaus. Now, the thrust here is to interpret the tectonic signatures in order to derive the history of formation and evolution of crestal plateaus. And there have been three different types of models. Those that are hot models, where rising mantle plumes or lava ponds or even a bolide model create a very thin lithosphere that thickens over time, and the deformation records that thickening of the lithosphere. There are cold models where the crust has bunched up together over downwelling cold plumes, and the accretionary models. Mapping, yes, so the mapping and determination of timing of small-scale grabens, some have dubbed them ribbons, has been a key issue of tessera and understanding the formation of tessera and crystal plateaus. And you can see the interpretation here of Gilmore trying to show that the small grabens are late stage features, while Hansen interpreted them as early stage. So this is a key issue that we need better resolution data. Others have implied that a late stage crystal relaxation of the plateaus is a driver for the formation of the late stage tectonic features such as grabens. And I modeled this with Roger some time ago and showed that relaxation depends on both the state of the compensation and the rheology of the crust. So a plateau can either relax while withholding its plateau aspect or becoming more domical, depending on the viscosity structure, but that's only occurs if the plateau is fully compensated to start with. If a plateau is formed with rims, it'll tend to withhold to its rims signature. And if a plateau starts with a lack of full compensation, the initial isostatic adjustment will lead to the formation not only of rims, but also troughs outside of the plateaus. We don't see those troughs, but they could have been easily embayed, for example. One of the key issues is that either modes of relaxation, fully compensated or with the initial isostatic adjustment, do not explain all the tectonic features we see in crustal plateaus. More recently, named Nemo and Mackwell, used the topography of plateau and the different viscosities to constrain the potentially different rheologies of the crust as they go here with the time scales and heat flux with the different rock types and hydration states. So plateaus may be a way, and their topographic signatures may be a way of constraining the crustal composition. Speaking of the subsurface, currently plateaus are essentially compensated by a thickened crust, meaning there's a crustal root. And inverting the gravity data shows that, as we can see here in this Mayan and Bazarek model here, data and model, fitting model. However, we can only interpret down to about 300 kilometers in scale, which is approximately the size of the plateaus, the radius of the plateaus, because of the resolution of the gravity data. If we want to understand what the crustal root looks like, for example, if the margins are due to thickened crust, even thicker crust, and that help with the interpretation of how these margins were created via either isostatic adjustment or accretion, we need better resolution of the gravity field. And just to make things exciting, recently some other workers have looked at tessera and tried to understand the range of signatures that they see, the range of features they see. And some recent interpretation by Kauja et al. Indicates that not only you have a tectonic driver for the surface morphology, but perhaps a fluvial one as well. We know that on Earth, there's an interplay between fluvial signatures and tectonics, but they are also here interpreting the possibility of a fluvial signature to tessera. So I think it is great that after Magellan and now gearing up for the new missions to Venus, we were able to, via better analysis techniques, to reinterpret or reprocess Magellan data, better modeling, and novel interpretations, just to shake up some of the paradigms that got so entrenched at the end of Magellan, and will perhaps it is re-energizing the Venus field. Even if some of these interpretations are rather uncomfortable or sporty, in my opinion, it is good to have this re-energization of the Venus field. But I think that we're starting to move away from that thick-lid regime where the lithosphere is stagnant to one that is perhaps squishy currently. And that is certainly going to have an impact on whether we interpret the evolutionary path of Venus, whether it has undergone a catastrophic resurfacing a number of million years ago, or if it's ongoing an equilibrium resurfacing. But for certain, Venus activity is increasing with the new missions and the new papers, as I mentioned. And here, just a review of Veritas with its better topography, better gravity, better imaging. We're certainly going to be able to look at Tessera and other features in a lot more detail and perhaps close some of these first order questions that are still remaining. And that's it for me.